All right, so
I'm sorry, which one did you say download?
it's called BLS URS vetting.
Okay.
Do y'all have it?
Yeah. No, not even yet.
Okay, so as you can see, don't be afraid by this number here, 27 slides.
Okay.
It's not that much, actually. So today we start our actual letters. Before we start, though, anybody that wasn't here last time wants to go ahead. What's your name and?
Oh, I'm Luke McCourt.
Okay.
I attended online last time.
Okay.
Good. Here today.
Got any questions that you want to bring up before we start?
I'm okay. Thank you.
Yeah, you're good? Okay. So let's start. Let's get into it, right? So today we're going to have our very first actual lecture where we actually get to cover some material. So we start with our conversation of vetting data as per the syllabus and like what we want to do. So the story of vetting data has to do with ensuring that the data that you have is of quality, okay? Lots of people, they collect a lot of data, and then once they have a large data set, they just dump it onto the computer and then just start running numbers. And I think that's one of the downfalls of the age of computer, is that everybody has computers available, and it's very easy for you to run a data set these days, right? When I started my graduate career, computers were still, I don't want to date myself too much, they weren't available, they weren't as readily available as you guys. Like the notion of bringing a laptop to class, for example, was not, something. But if you wanted to use software like this, you would have to go to the computer lab at the university, and then there was a sign-up sheet, you would sign up, and then you would get a slot. Right? So you'd come back a month later, and then you use it for like an hour, and then that was it. Today, in the middle of this class, you are all going to have the computer, like the software in your hands. And the downside of that, like I said, is that it's very easy for you to just let me just run the data to see what I get. It's literally like you press enter and results come out immediately. In my time, it wasn't that immediate, right? In my advisor's time, you would press enter, and then you had to wait a month for the results to come out. So things have changed. Anyways, the point that I'm trying to make is, it's very important that you don't fall prey to that you don't, skip steps. It's important that before you do any analysis, right, it's important that you look at the data and you ensure its health, right? So that's something, Zach took my class, my undergraduate level class, and that's something that we never do in that class. We never analyze the data because at that class, we never vet the data because in that class, we just don't have any time for it. In here, we're going to spend today discussing that, okay? Before we get into it, though, there's a question that is worth asking, and it is, since we're talking about vetting data, looking at the health of data, the first question, most obvious question, is what is data? So can somebody tell me what data is? What does this say?
No, that's just something that's yeah.
We're in here together.
Yeah.
Okay. All right. So what is data? Someone?
Information.
Information. Okay. True, but very vague. Let's do
Something that can be analyzed.
something that can be analyzed. Okay, good, but vague. Or at least not what I'm looking for. Anybody else? When I say data, what do you think of?
Numbers.
Numbers? Okay, good. Anybody else? So numbers is a good start, right? Right? For the sake of this class, numbers is a good start, but you have to think a little bit beyond that. By itself, a number is not exactly data. A number is only data once it follows a specific context. Right, so for the purposes of this class, data is any quantification of a matter of interest or a concept. So picking up on this idea of a number, right? So think the number 7. The number 7 by itself is not data. The number 7 by itself is just a number, right? It's greater than 6, smaller than 8, but by itself, it doesn't mean anything. When I say 7, each and every one of you will think of a different thing. 7 days of the week, 7 deadly sins, whatever, right? That's not enough. So by itself, the number doesn't carry any meaning, so it's not data. But once that number is attached to some sort of concept, and that concept is represented by that number, then that number becomes data. So for example, take a question that scientists have been trying to figure out since the beginning of science, like how do you produce happiness? Like what's happiness, right? So lots of people study the notion of happiness and how is it that you can improve somebody else's lives? How can you help people get happier, right? So right there is a question of social sciences, cause and effect. This causes you to be happy. This causes you to be unhappy, right? So if you want to do that study, which by the way, there is a study that's been going on for that. It's more than 30 years old. It's held, Harvard conducts it every year, it updates it. So if you're interested in that, we can talk about that later, or on the side. But anyways, when we attach this notion of happiness, and we give you a context, then that number 7 then becomes a sum. Like for example, if I give you a scale, where 0 is the most unhappy you can possibly be, and 10 is the happiest you can possibly be. And now I say, what's a 7? Let's say you are at a 7. Now, hopefully, like you're all thinking about the same thing, meaning you're probably reaching a very similar conclusion, right? If I say this person is at a level 7, what do you think of this person? Is this person very unhappy?
No.
Not really, right? Is this person like fully happy and most happy? No. If you had to say this person is happy or unhappy, what would you say? They're more towards the happy, right? So notice that now the number 7 has meaning, right? So we went from turning the number 7 from simply a number to data. It's now data because it is a rough quantification of a concept, right? A concept of happiness. In this class, this is all that we're going to be doing, right? We're going to be taking these concepts that we're interested in. Each one of us interested in a different concept, but in general, we're going to take these concepts, we're going to quantify them in some scale, 0 to 7, 0 to 10. The most common one is 0 to 7, but it depends on what we're trying to quantify. Like if we're talking about money, then it's like thousands of dollars. If we're talking about age, then we're talking about years, right? We quantify these concepts, we turn them into something that can be easily translated into a number, and then that becomes our data. Yeah, do we understand this idea of data? So when I talk about data, I want you to think about this idea. Okay, we have a concept in mind. This concept by itself is not necessarily a number, but we went through some exercise, some magic, we put through this concept through the ringer, and we came out with the quantification of it that allows us to then turn it into a number. Because the computer, again, is only going to take numbers, right? A data set, for the purposes of this class, is one or a series of variables, right? So what do I mean by that? If I want to quantify the notion of happiness, then happiness is our variable. And we're going to have a series of observations of that variable. So if I'm doing a study on happiness, I'm going to go and ask 50 people, 100 people, 1,000 people, what have you. But I am going to take this concept, turn it into a scale, and then I'm going to collect all these observations. And that will become a variable. So the simplest possible data set that you can have is a data set that contains one variable, and that variable contains one observation. That would be the simplest possible data set that you can have. Like for example, if I'm interested simply in happiness, like what's your level of happiness, and I go out there and I ask one person, what's your level of happiness? They give me a number, and then I'm done. Right? That is a pretty useless data set, but it is a data set by concept, it fits the definition of a data set. What we want is actually lots of observations. If you remember from our discussion in the previous class, what we want is lots of observations so that we can analyze it and then throw away that observation, throw away all those observations and come up with some description of it that will be useful for others. Remember the story of 1.8 billion people, 1.8 billion Muslims pray 5 times a day. So we go out there, the variable begin how often do you pray? We go out there, we ask 1.8 million people, Muslims that is, how often they pray. They say, oh, I pray 5 times, I pray 6 times, and then the average is 5. Then I throw away all those 1.8 billion observations, and I just report to you that the average number is 5. That's a story of data, right? So now we're getting a little richer data set because we have one variable, but we have, in this case, in this example, 1.8 billion observations. Yeah? For the purposes of this class, since we're trying to explain stuff, we're trying what we want to do in this class, if you want to simplify with a sentence, is this causes that. This class is a class that will empower us to use data in order to effectively say, this causes that. Right? So if we want to say this causes that, this is a concept and this is another concept. We need 2 variables, right? One to represent this concept, one to represent that concept. Does that make sense? So the data sets that we'll be dealing with are going to be a little richer because they're going to have, hopefully, 2 variables that we can then connect with the analysis. Right? If you want to do good work, responsible work, chances are you're going to need even more than 2. Right? Because especially in the world of social sciences, nothing is explained by one factor. Right? Everything out there is explained by several factors. So we need to include all of those things in the analysis. So, in this example of this study, the Harvard study that tries to understand happiness, they account for several things. They account for how much money you make. They account for what types of relationship you have. You have children. Are you married? What's your relationship with your children? Right? They account for your level of faith. Do you go to church? Do you not go to church? Do you have faith but you don't attend services? Do you attend services but your faith? So they account for several elements, and therefore, all of these elements, all of these concepts, they need to first be quantified. Right? We need to come up with a scale that translates those things into numbers, and then we need to collect them, and then we need to analyze them. Right? So first, we want to understand happiness, so we come up with a scale of happiness. 0 meaning super unhappy, I want to kill myself today. 10 being I'm so happy, I want to give birth today, multiply my, whatever. You get the gist of it. From really unhappy to super happy. Then we want to talk about wealth. Well, wealth is I'm so poor I can even pay attention, and super rich is I am so rich I hang out with Jay-Z every weekend. Whatever. We come up with a scale, hopefully not as bad as these that I gave you, but we come up with scales and we convert all of those things into numbers, create these very rich data sets, and then we go on to analyze them. Why are you not working? Come on. Right? So, statistics, I'm going to take all this data, we're going to feed it through a model, and this is, the reason this slide is here is to clarify a little bit of the language. So you're going to hear me say 2 things. You're going to hear me say a model, or you're going to hear me say the word estimator. In reality, they're not the same thing, but for the purposes of this class, they are the same thing. So an estimator is a more specific thing. There are several estimators. A logit is one, a two-step linear regression is another, an ordinary regression is another, A survival regression is another. So these are all different types of estimators. But what we do is we take these concepts, we feed them through an estimator, the appropriate one, which is I'll teach you here, and then the computer is going to spit back a bunch of numbers, which we will interpret as evidence, and we will use that to back up our argument. Right? So from beginning to end, we have an understanding of something that we want to prove. I want to say that this causes that. Everybody here has a project that they're interested in, or an NGO that they want to work for, or a cause they want to defend, right? And all of those things are based on this idea that this causes that, right? If we fund shelters, homeless shelters, people will do better. If we give more money to the military, we're going to perform better in wars. If we extend Medicare to everybody, then there will be less disease in the country. If we extend Obamacare, if we force everybody to wear a mask, people are going to be unhappy. Whatever, everybody here has some causal plan. This causes that. As we do this, we see that. So, quantify that relationship that we're interested in. That's what we call modeling. We estimate it. Computer says, oh, here's a bunch of numbers. You're not familiar with any of those numbers yet, but you will be very soon. The computer's going to spit out all these numbers. You're going to know what to do with those numbers. You're going to say, look, I was right. You see, there's a relationship here. All of this causes that, evidenced by this number, and that number. Right? So it's like I'm fast forwarding 15 weeks from now. 15 weeks from now, you're going to have an idea. You're going to have a data set. You're going to churn it all through the computer. The computer's going to spit up a bunch of stuff. You're going to look at it. You're going to say, wow, I was right. This does cause that with this amount of precision, with this amount of direction, this magnitude, this level of certainty. If we increase this by this much, we should see this increasing by that much. If money causes happiness, which people love to say it doesn't, but people that don't have it, if that's true, then an increase, if I increase your salary by $100,000, then I expect your happiness level to go from 6 to 9. Right? So you're going to be able to give me an expectation of jump, of variation. Right? If I cut your salary by $50,000, then your happiness is going to go from 7 to 6, or to 4, or to whatever. Does that make sense? This is what we're going to do in class. Now, before we can do any of that, we have to make sure that the data that we have is healthy. You can't just put any data on the computer and do it. The computer does not know the quality of the data that you feed it. Right? So the computer is very naive in that sense. It's just going to assume that this is very great quality data. And it will spit results regardless of the quality of the data. In other words, the computer has no red flags to say, hey, guess what? This data looks bad. Right? So it is your job to examine the quality of the data before you run it. It's in very few cases that the computer will actually not work because your data is unhealthy. In other words, your data has to be very, very unhealthy for it not to work. I mean, it literally has to be crap. It has to be horrible for the computer to refuse to use it, right? And it's never the case. It's very often the case that people get away with terrible data, but it's never the case that the computer will crash on account of that. So because of that, you want to make sure that it's good, right? So this is a funny word to use, this notion of saying the computer, the data has to be healthy. You don't think of health, the healthiness of a number, right? So what does that mean? What does it mean to say that the data is healthy? Well, a data that is healthy is a data that has basically 3 qualities, right? So let me just pause for a second. So far, We spent 20 minutes talking about what we're going to do and how it works. Today, now, as we're entering into the nitty-gritty of the lecture, which is how do we know that the data is healthy? And we know that the data is healthy when it has three things. It has signs of convergence, it has healthy dispersion levels, and it has non-suspicious outliers. If a data set has these three things, if you've looked for these three things and you've reached these three things, then your data is good to go. All right, so if you have a data set where there's absolutely no signs of conversion, the dispersion is irregular, and there's a bunch of outliers, you're in trouble. That's real crappy data. You should stop there. Like, there's no point in doing any analysis with data that doesn't have, if a data is missing these three things. Never the case, or I haven't run across a situation where actually you have a data set that is missing all these three things. This would be like a patient that has coronavirus, cancer, and HIV all together. Like, that would be, you don't see that, right? So if you actually see something like this, then it's a very clear sign that you should step away from this. Chances are you're going to encounter data that is that has a little bit of one and not the other, right? So you're going to have to exercise some decision making. You're going to have to, oh well, the dispersion is not great, but it's not terrible. And so I'll give you like parameters for us to understand kind of like how to deal with it. Do you understand this? Three things. You have to have these three things. All right? So let's start with convergence. For us to talk about convergence, we have to understand the notion of centrality. Centrality has to do with, well, why don't I ask, what do you think of when I say centrality? Middle, great. What else? Central state? Is that what you think of? What is centrality? Anybody else? Middle is
It's
a good
central
answer.
to the problem.
What?
Is it central to the problem?
No.
Oh,
That's a
okay.
good point. Centrality as it gets to the center of the problem. That's a good way to go. I like your thinking, but we're now strictly talking about numbers. Like, what is a data? When I talk about the centrality of the number or a series of numbers, in this case a variable, what are we talking about? Averages. What else? We're talking about three things, right? There are three measures of centrality. The most obvious one is the average, also known as the mean, okay? But there's two others that are less prominent. You're probably familiar with them, but they don't help us much other than kind of like show us that that convergence exists, right? So what do we mean by our centrality? So you take a data set and then you just put it in order from smallest to largest, or from largest to small. It doesn't matter, as long as you put it in order, right? So our running example here is happiness. We ask 100 people how they feel, and we're not going to get those answers in order, right? It's not as if the first person is going to say 1, and the second person is going to say 2, and the third person is going to say 3, right? We're going to get various answers, right? So your data set is going to be 1, 7, 12, well, not 12, 1, 7, 9, 0, 0, 2, 5, right? It's going to be all over the place. So the first thing you want to do is you want to put it in order, right? So now it's like 0, 0, 0, 1, 1, 1, 1, 2, 2, 2, 2, 2, 3, and it's all in order, right? Once you do that, then you're going to look at these measures of centrality. The first one being the mode. What is a mode? The most common, right? So, anybody here speaks French? Tu parles français. Qu'est-ce que mode? What is the magazine mode?
C'est la fashion.
Fashion, right? So, mode is fashion, the most fashionable. What is a fashionable number? The one that shows up the most, right? So is a very obvious thing, right? So you can think of mode as fashionable. Think of the magazine, right? I could use this 20 years ago because of Madonna's mode. Today, kids are like, who's Madonna? So anyways, that's the most fashionable number. So the most common number in the data set. So we have all these observations, right? All these responses, 0, 1, 2, 6. But we see in general, people are at a 6. See a bunch of 6s. Well, that's the mode. That's the number that we see the most, right? Then we have the median. What's the median?
What's in the middle, basically? Yeah,
Just
the
put
middle
it
number.
down.
It's the one that's in the middle. So the median is a number that divides the distribution in half. There will be as many observations to the left of it as there are to the right of it. So basically, if I have a data set that is one, 2, 3. Can you see it over there? 1, 2, 3. Right. So if we have a data set that's 1, 2, 3, this is very simple, but this is the number that divides the data set in half. There is one number to the right of it and one number to the left of it. Yeah?
Yeah.
Very straightforward. The median, when you're driving, what's the median? The thing that divides the road in half, right? So it's the same thing. It's the number that divides the distribution in half. So it's an interesting thing because the median is not necessarily the middle value. It's simply the middle number, right? So if I have a data set that is 1, 8, 9, the median is 8, but the average is going to be what? 18 divided by 3, 6. So it's not exactly the same. Whereas if I take this 1, 2, 3, that's 6 divided by 3, it's smack in the middle, right? And this is kind of like what we're talking about when we say convergence. Let me give you the last one, and then we'll wrap this up, right? The last number is the mean. What is the mean? This is the one that you're most familiar with.
Is it based on the average?
It's not basically the average. It is the average. A mean is just another number for just another name for the average. And what is that?
Sum divided by the quantity.
The
Yeah.
sum divide. Okay, that is the definition of it. But I want the understanding. I want you to explain what is it the mean gives you.
The relative scale of the data set.
No. That's only of a healthy data set. A mean gives you more than that. And it also works for unhealthy.
Like for instance, if you do it and it's like a decimal, you know that it's like.
No.
It's like if you
Are you
took,
Milo? Is that
yes,
Milo?
yes. If you took like every record that you had, it would be what you would have, like, to equal the entire, I'm kind of saying what she said back there, but
No.
you add that all up, it would be the totality of everything.
No. Oh, great. Hey, don't, just because I say no to you, don't stop talking, man. It's okay. What's your name again?
Isabel,
Isabel.
it gives you a percentage that allows you to compare it to other data sets and other values.
No. No. Mind, these are all things, they're close to, but they're close to, they're either true or close to true, but they're not the essence of the mean. The mean has a very powerful quality built into it, and it's called simultaneous proximity, okay? It's a very different concept to explain in English. It's even more complicated to explain mathematically, and this is my best shot at explaining it to you. And once you understand, it's very obvious, but it's not something that comes out off the bat. So since I'm not past being stupid in order to buy some clarification or looking foolish, we'll use this example here to just illustrate what is it that the mean gives you, right? So everybody here familiar with the notion of the bouquet in Christian weddings, right?
Yeah.
Right, where the bride She takes her bouquet, she goes to clear it, to a very clear area, she goes to the front, turns around, and tosses it back, right? To a bunch of women in the back. Woman who catches the bouquet is the next one who is going to be married, right? My wife hates this example because she says it's demeaning to women, and because the idea is that it's like a woman's goal is to find a husband, right? That would be a very important moment because she gets a sign that her husband is coming, right? So, anyways, let's forget all about that, right? This Me Too. Let's forget this in this Me Too area. I'm not in favor of bouquets, right? I understand that they're oppressive, but let's just use the example, right? We're all familiar with this. So let's imagine a situation where we're all in this wedding, we're all dying to catch that bouquet, right, equally, and the bride is going to toss the bouquet. The bouquet is going to come, she's going to toss it in one of these 4 spots. In real life, it could go anywhere, right? But that would make our lives more difficult. This example would more. So let's just suppose that she's going to toss it. Like, here's the crowd. You see her bouquet of flowers. This shows why I went to stat school and not drawing school or art school, right? She's going to toss it here, 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 or here. 4 spots, right? So you know it's going to go in one of these 4. You don't know which one, but you know it's in one of these. So the question is, where are you going to place yourself? Imagine that you really want it, and don't tell me I don't need a man, and I make my own. That's not the point of this example. Where are you going to place yourself? Come on, you got it.
In the middle, the second
Two
one.
middle axis.
Yeah.
Where? Here?
One of the
The
two
next
middle
one.
axis.
Here.
Somewhere in there.
Okay. By show of hands, how many of you are going here? You do really want it, huh?
Good God.
Right? That is the best spot right there. Alright? So why? Why do you want to place yourself right there?
Probability. Based on where she's standing and where if she has a fairly linear throw behind her and doesn't go completely cattywampus, she'll be all right. You can get it there most likely.
Depends on the hand she's using.
That's true. That's all correct. But I want it in even simpler English.
In the middle. It's the closest.
Okay, it's the middle. Who said the closest? It's the closest. So
To the blue.
this point is the closest to this point? No, this point here is the closest to this point here. So no, it's not this is not the closest. It's very good intuition though. Very good. You missed by very little. Anybody? Pick up on what she said, add a few words here and there.
It's because you can take
to the original, to where it's originating from.
True, but that's not the reason.
Because if you're in the middle, then you're the same distance, like either way from each side. So if they throw it and you want to run one way or the other, then you have the best odds of going either way.
So that's your probability there. I'm sorry, what's your name again?
me.
Yes,
I'm Sue.
Sue. So okay, so you're picking up on Sue's probability seat. That's the probability. So both of you are exactly right. And you're right there in that it's close, but you're not closest to anything other than you are closest to all possible points, right? So if you're not picking this up, if you're a man and you're just like, what is this? My oppression comes in a lot more straightforward ways. Right, then this is LeBron James, and then he's gonna pass. And how are you gonna block LeBron James? Right, you're not. But right? But what's the story here? Well, the story here is that if you're sitting here and she throws here, all you have to do is this, and you got it. That's great. But if she tosses it all the way here, forget it. You don't even try to get it, right? Because you're not going to be able to. If you're sitting here and she throws here, same thing, great. But then you're not going to be able to get it to over here. Whereas if you're sitting here, right, then you take a little step to the left, just like to the left, y'all, and you're right there. To the right now, y'all, and you're right here. Now, if she throws it over here, it's 2 to the left now, or 2 to the right now. But this is the point where you're simultaneously closest to all possible points, right? Which translates to, in English, this is your best guess. The mean is always your best guess, right? So if you want to be right, meaning if you want to get this, be on the right spot to get the bouquet, then you want to be at the mean. And the thing about the mean that is so powerful yet maybe counterintuitive is that the best place for you to get the bouquet is a spot where you know 100% she's not going to throw there, right? It's counterintuitive. You want to get it, and you're literally standing in the place where she's not going to throw, right? Your intuition would be to go right here, like you said, right? Because I know she's going to throw. There's a good chance she'll throw here. So that's the thing about the mean that is very powerful for statistics, and it's a driving force in statistics. As a matter of fact, if you want to be very technical, all of statistics is a mean. All of it. It's just that statistics sometimes piles means on top of means on top of means, right? So I'll take a data set, I'll take 3 variables, I'll calculate the mean of every variable, I have 3 means. Then I'll calculate the difference between this variable and that variable, and then I have 2 differences, I'll calculate the mean of the differences. Now I have a mean and a mean of the differences. Then I take the mean of the differences, multiply, and then I have a mean of the quadratic differences, and then for that I got a square root, and I'm back to the mean of the, and it's all a mean. They're means, because means are the best guess. And if you go back to the beginning of this lecture, what's the job of the statistician? It's to reduce uncertainty. And you reduce uncertainty by making the best guess. So the mean is how we're going to get there. Right? So what is convergence? Right? So how do we know that the data set is healthy enough? The data set is healthy enough when the mean, the mode, and the median are really close together. So that's the first sign that you have a good data set, is that it's showing good signs of convergence, right? So what we have here is a data set 1, 2, 3. The median is 2. That's the data set. That's the point that divides the data set in half. It doesn't have a mode, obviously, right? But the mean is 2 and the median is 2. They're the same number. So that's good convergence right there. Here, we would qualify this as a healthy data set. This has a median of 8. Doesn't have any mode, again, because there's only 3 numbers. It's a very simple data set. But it has a median of 8 and a mean, or an average, of 6. Not great convergence. So this is definitely a healthier data set than this one. Now, I'm using these two over here. I'm using these 2 just to make it palatable, right? 3 numbers is simple. We can all look at it. We can't learn anything from 3 observations, right? So, we're not going to get good convergence on data sets like this. But when you start having large data sets, 500, 600, convergence on healthy data sets, they become very obvious. Now, they don't have to land on top of each other smack on, like 2 and 2 and 2, like median 2, mode 2, average, mean 2. It doesn't have to be like that, but it has to be close enough. And you have to be the judge of what close enough means. If you have a data set that ranges from 1 to 1,000, and the mean is 500, and the median is 499, and the mode is 501, right? They're close enough by 1 on a range of 1,000. That really is not very much. You can all but say this data set has converged. Now, if you have a data set from 0 to 10, and then you have a mean of 5 and a mode of 7 and a medium of 3, they're only 2 apart from the mean, but on a scale of 10, that 2 becomes damning. So you have to look at the entire data set, look at the picture of the whole thing, and then see how that relates to the convergence level. Do you understand convergence? Are we good? It's a simple idea, right? But it's an important one. Data that is healthy has to show signs of convergence. All right? Okay, so the first thing is convergence. The second thing is dispersion. We talked about it before, right? 3 things. First, convergence. Second, dispersion. What is dispersion? So if convergence, right, this is an example of a data set. Just to be quick here, here's a data set, right? Oops. What is this data? I think it's cholesterol levels, right? So 240, 225, 225, 226, 230, 225, 220. So clearly this is not ordered. So this is just data that's been collected. So the first thing we do is we order, and we turn this data into a distribution, right? We just put it in order from lowest to highest value, starting at 220, ending at 240. The mode is 225, shows up 3 times. 1, 2, 3. So that's the mode, 225. Medium, that's 225 right here, right? This one. 1, 2, 3 numbers to the left of it. 1, 2, 3 numbers to the right of it, right? Mean is 27.3. So, to me, this looks like a pretty good, well-converged data, right? The mean is 227. That's your guiding force. It's the most powerful one. And then we have these 2 numbers that themselves have collapsed into 1 and are really, really close to, really close to 227. Yeah? Okay. So, again, no rule of thumb, but just a little common sense will get you there. Then we start talking about measures of dispersion. So, a measure of dispersion, first of all, dispersion is another type of mean, another type of average, and that's the average of how far do points fall away from the average. Let me repeat that because this is where stats gets confusing on account of language. Dispersion is the average value of how far a point falls away from the average. So what does that mean in English? Let's say we have a data set. The average is 10, right? Now I get the entire data set in my hand, all the variables, and I look at the first observation, the first person. They gave me a score of 12. So 12 is 2 points away from 10. Yeah? 10 is your average, 12 is the individual observation. 10 is your average, meaning I took all the observations and I calculated the average. I got 10. The first observation was 12, so I'm 2 points away from 10. The second observation is 9, I am 1 point away from 10. The third observation is 13, I'm 3 points away from 10. And I do that for every single observation. Yes? So now I have quantification of how far each point falls away from the average. Yes? Please nod your head. So if I have all these numbers, and I calculate the average of it, now I have the average dispersion from the average. What we want is for data to be healthy, or for healthy data for data to be healthy, its dispersion rate has to be less than the mean or the average. So if you go through this entire rigmarole of computing the average, and then looking at every single observation, and computing the distance to the average, and then computing that average distance to the average, you're gonna get a number. And if that number is higher than the average, your data is over-dispersed. And over-dispersed data is unhealthy data. Okay, we don't need to get into why it is, right? We just need to understand that it is. It's a red flag for you. There's something wrong with this data. Either it was collected poorly, there's not enough data, or the concept itself is not suitable to be used in statistics. Right? So we, again, are not going to engage in the process of calculating the value of dispersion. There are several values of dispersion. The most common one is the standard deviation. You've probably heard of it, you are familiar with it, but if I were to press you as to how to compute it and why is it important, you probably wouldn't be able to explain it to me. Okay? The beauty of this class is that none of that is necessary. You don't have to understand it, like why it is and what it is and how to get there, other than you need to understand that if that number is higher than your average, you're in trouble. Right? It's a much simpler thing. It saves us a whole day of like this plus that, square root divided by n minus 1, multiply. Right? Nobody wants to do that. That's why we have our beautiful computer friends, right? Agent Smith will do that for us. Okay? So, first thing we want is we want converged data. Second thing that we want is we want non-over-dispersed data. So we want healthy dispersed data, right? Less than the average. Third thing that we're looking for is attention to the outliers. Data sets will always have outliers. You just have to pay attention to what they are. So before we move forward, let's just clarify the obvious. What is an outlier?
Not the norm.
Yes, but again in English.
The exceptions.
It's usually one that doesn't match the data set itself. It's out in left field.
Or right field. Perfect.
Whatever.
It's a number within the data set that does not really match with the other numbers. It's not really close to the other numbers.
Absolutely. So you're always going to get that. And therefore, it's a tricky thing for us because it's very natural that your data set will have outliers. Rule of thumb is if you have a data set, a data observation on your data set, if you have a data point that is 3 standard deviations away from your mean, that is usually an outlier. So what do I mean by that? Let's say that you have a data set and the average is 7. Okay? That's your average. Your standard deviation, mu is mean, Greek. We're just going to put average because this is not a class for smart asses. Right? Then what is it? Rho? No. Sigma. Etc. We're just going to call it SD, right? Much simpler. Standard deviation. Your standard deviation is 2, right? So you're good as far as over dispersion, right? 2 and 7, you're good. If this is rule of thumb, you got an observation 3 standard deviations away from 7. So that's if you have a 9, that's 1 standard deviation away from 7. And if you have an 11, that's 2 standard deviations away from 7, right? If you have a 13, you are 3 standard deviations away from 7. This 13 over here is point of concern. Okay? Now, that's not enough. If you're going to get exactly 2, right? That's not enough. If you're really far from 2, if you're 3, not 2, 3. If you're really far from 3, if you're 4 or 5, you know it's a standard. It's a whack job of a number. If you're really at 3, you're going to have to do something. Right? And this is the story of suspicious versus non-suspicious outliers. Right? And what to do. So you have a data set. What you want to do is you want to start looking you did your convergence, you did your dispersion, now you're looking at these outliers. You're gonna start looking for suspicious versus non-suspicious outliers. First of all, if you've got a data set with no outliers, yay, then you're off to the races, you can start doing your analysis, right? Now, if you've got an outlier, the first question you have to ask yourself is this a suspicious outlier versus a non-suspicious one, right? So what is a non-suspicious outlier? A non-suspicious outlier is an outlier that is clearly an outlier. However, by ways of understanding what we're talking about, by ways of being aware of the concept at hand, right, way back when. So we started with happiness, remember? And now we're talking about convergence of numbers. So we've traveled quite a lot, quite a path, but we never lost track of what we're trying to get here, happiness. So if we are really aware of happiness, we can go back to that concept and kind of like make sense of it. So let me give you an example, moving away a little bit from happiness, but still very palatable, right? Imagine that we're trying to figure out the age of people enrolled in an undergraduate level class, right? So I take, these are actually real numbers from my 3020 class. And you take a look at it, right? You have, the average age is 21, right? You got your juniors, you got your sophomores taking the class, you got a few freshmen who just jumped in off the deep end, like already in a high level class, right? But on average, what you got is like a bunch of 19-year-olds, 1, 2, 3, 4 19-year-olds, and 4 20-year-olds, and 21-year-olds, 22, 23, and then you got 24s, and then you got a couple kids 25, but then you got 15, and you got 55, right? These numbers are clearly outliers, yeah? So then I'm just going to take this data set and throw it away. I can't use it. Yes or no?
No.
No, can I not? I can't use it, or no, I can use it?
You can use it.
So why is it that I can't use it? What's happening here with these two numbers?
They can be explained, like you said. The 15-year-old can be explained because they left school a little early. And then the 55-year-old can be explained because he came back to school late.
Okay, so what we're talking about here, that's great. That's the answer I'm looking for. But we can even add more English to it. So this is, you bring another professor in here, and he's going to have, I have a bunch of tattoos of my kids here, and I'm zealous of them. I don't, so if you're seeing it, here, let's get this out of the way, because I feel bad. So anyways, what's the 15-year-old? 15-year-old is Ohio's college credit for high school. It's a program in Ohio, right, that if you attend college at Wright State, your school district pays for the tuition, right? So it's an incentive to get kids to go attend school early. And every class, we get one of those kids. It's usually an overly eager kid who's only 15 and he usually kicks ass. Does better than most kids because, again, he's overly eager, right? So, yeah, that's not your average, student, but it's not as though, it's nothing crazy. And this kid usually, like I said, behaves like these or better. So even though this is a different number, it's still a good number. It is far away, but it's not suspicious enough that I need to toss it out. All right? There is still quality here. I can still use this observation in my study because it's still representative of what I'm trying to understand. Yeah? Here, again, if you're a professor, you know exactly who this person is. Who is this?
The professor.
No.
Either somebody
It's
that's
me. I'm not quite here, but I'm getting it.
it's usually somebody that either didn't finish and coming back, or they get like a different degree that changed careers or something.
Yes, you're right, but I have a name. This person 9 times out of 10 is a GI but bill student, because Wright State has a deal with Wright-Patterson, right? And a lot of people, a lot of students, a lot of officers end their careers specifically at Wright-Pat because they know, they've been instructed by the military that if they end up in Ohio, Wright State will take them, and then they can just transition in, and then the military will pay for it, right? So again, this person is somebody who is just, in many ways, just as eager as this kid. And, it also has the benefit of life experience to perform better than most of these kids. So again, it's a usable, it's a number that's off, but it's not off in the sense that we have to disregard this person's experience. So it's a valid number in a sense, even though it looks off, right? And this is the thing that I told you, that the computer won't pick, right? The computer doesn't know about Wright State, and right, only you know as the person interested in whatever it is that you're studying. And this is the beauty of it, because as a social scientist, it's got nothing to do with numbers, it has to do with your experience, right? So if you're a social worker, you see a kid coming in the room, right? You know exactly what's going on. Like, this kid coming from this neighborhood, it's this ethnic background, the problem looks like this and whatnot. And then this is another kid, it's another immigrant community coming from another part of town. It's a different set of problems. This has to do with the experience that you have of the concept itself. So this is where social sciences meets numbers. Every single number here needs to connote, it needs to have a meaning beyond the number itself. Like this number has a meaning for me. What's this number? 19.
Average.
A student?
What kind of student?
Freshman.
Freshman. This is the freshman, it's 19. Right? This is a college credit. This is a GI. This is a sophomore. This is a senior. So again, you've seen the original Matrix, the movie Matrix. How many of you have seen the original one? Oh, that's when you feel 55. So there's a scene in the original movie where, that famous, like the numbers dropping, and the computer programmer, he's like, look, she's a brunette, right? And he's like goggling over this brunette, and all you see is these numbers fall. And the statistician watching that scene gets all giggly. He's like, yes, the numbers have meaning. It's like, it's how I see this. I see a young kid, here I see a GI person, right? So it's a very romantic way to look at it. And anyways, so you want to have this understanding, right? This is a non-suspicious outlier. This is a suspicious outlier. Imagine you have this data set, and then you got this number over here, 135. What is this number here? What is a 135-year-old? He's dead. He's been dead for 4 years at least. Right? It's either Baby Yoda or Yoda himself. Right? It's a typo. Right? So this number is really suspicious. Like, this is clearly wrong. Like, you can take this number over here and literally delete from the data set without any concern that you're losing important information, right? If you delete this point over here, you're losing useful information. If you delete that point, you're no longer learning something about that person that's a GI, coming back from the military with life experience and so on. Here you delete this point, you're losing information about young go-getter kids and so on. You delete this, you lose nothing, because how many of you have ever met a 135-year-old, right? So this is the part that, you're gonna, again, have to exercise your social science awareness. if you have a data set that looks like a combination of these, meaning in addition to this 135, there's a 55 and a 15, then you keep the 15, you keep the 55, and you delete the 135. Make sense? Great. So this is your vetting of the data. This is you checking the data set for its usability. If you have a data set that shows convergence, has a healthy dispersion, and either doesn't have outliers or only has outliers that can be accounted for, then you have yourself a good variable that you can use. And you do that for every variable that you have. So we go back to our example of happiness. We are trying to understand what causes happiness, and in my very crude example, money causes happiness. So you're going to have two variables. One, a variable of how much money you have, and the other variable is your level of happiness. You're going to vet those two. Right? If both of those match the levels of a healthy data set, if they're both dispersing all right, they're converging all right, they have no outliers, then you're ready to use them for an analysis. Do we see that? Do we understand that? What kind of questions do we have? No questions? Yeah.
Like a hypothetical, so if you're doing your money variable, and say somebody states a sum that is abnormally larger than the average, say they won't be happy until they get 5 million. Everyone else is, in the hundreds of thousands. Do you still keep that sum because it has a backup, like a reason for being there? Or, because it's not suspicious.
So that's an excellent question, right? It's a very tough question. So first of all, your language, let's appropriate it. You're asking how much money they have, not how much money they need to have, right? So we want to figure out if money leads to happiness, right? So if that assumption this is a working assumption, but if it's true, then people that have a lot of money are going to be very happy. People that have no money are going to be very sad or unhappy. Yeah? Mm-hmm. So what you do, if this assumption is correct, then everybody that has money is going to be happy. Nobody that has money will be happy. So what you're hoping to observe as you go out there and you start asking is what? What expectation do you have of what you are going to observe?
They correlate.
Yeah, but what kind of answers are you going to get? How much money do you have?
Right now,
Right now.
I don't carry cash, it's 0.
0. So the expectation that I have is that Milo is an unhappy sucker. Yeah? How much money do you have? 100,000 in your pocket? My assumption is she's very happy. And that's going to carry for every single person that I ask. If they have a lot of money, they're going to be very happy. If they have no money, they're going to be very unhappy. That's the correlation that you're talking about. Yeah? So that's the expectation of correlation that I have. So if I get you correct, your question is, what if somebody tells you that they have $5 million in their pocket? Yeah? And you're like, who the hell carries $5 million and can even put it in your pocket? Right? Well, I would toss that out because that seems very unreasonable. However, if the scale is how much money do you have in assets, house and car, then $5 million is no longer, I mean, it's still a lot of money, but it's no longer like a, yeah. So I guess that's not the answer that you're looking for. The answer is it's very specific to the situation in which the data was collected, right? So, do you know who the Migos are? Migos? The rap group.
Oh, Migos, yes.
So you know Migos, right? So go on YouTube and do a search for Migos on the car karaoke, right? You know what I'm talking? Anybody seen that?
Yeah.
So they're doing the car karaoke, and then what's his name?
James Corden.
James Corden says, I heard to one of the Migos guys, right? I heard that you don't trust banks and that you only have cash. And he's like, yeah, and he's making his rap look like, right? And he's like, yeah, I don't trust banks. And he's like, how much money, what do you mean, how much money do you have? And he opens a bag. And he starts like going through the bag. You have to see this, man. And he starts counting, and he has 200 grand in the bag with ones and tens. He's just like, so we live in a world now where people carry 200 grand worth of cash, right? And then Milo here doesn't carry cash. The reality is he doesn't have any cash, but he got caught, and he's like, I don't carry cash. He just doesn't have any. But most people don't carry cash anymore, right? So it's a tough question, man. You're only going to be able to make sense of it if you're really steeped in the way, what's being asked, and really the minutiae of it. Are you asking how much money you have in your pocket, or in your bank account, or even like your net worth, right? Because your bank account, you could have no money in your bank account, but you could have 6 properties in Beverly Hills, and your net worth is really high. So these questions are really, really tough. I don't have a straight answer for you. I hope I didn't. I don't.
Oh no, that's okay. I just didn't know if you kept a number like that, but you're just saying be reasonable.
You have to be
Question you're
reasonable.
asking.
Okay.
It depends how, if you're asking like a baller, if you're only asking rappers, right? Lil Wayne and Migos and Jay-Z, then your ballpark starter should be 100,000, right? Whereas if you're asking college student, then your ballpark starter would be like $3, and you should be suspicious of any kid that has $35 in it, right? So, any other question? Great question. Any other question? You guys at home? Yes.
I know that you listed the 3, the convergence and the healthy dispersion and the non-suspicious outlier as a measures to evaluate whether the data is reliable or not. But I have another vision about this, is that, let's say if we take the concept of happiness.
Yes.
Okay. What about if we can evaluate that happiness itself? It cannot be measured because of lack of experience. For example, if you ask a young guy based on money, are you happy or not? And if he has money, he would say, yes, I am very happy. You go and ask him after he passed the age of 60, he realized, well, I was not happy.
Oh, absolutely. I mean, you were correct. So,
So my question is, for the person who gonna judge, who gonna make this judgment, I think he should have some knowledge more than statistics in order to overall evaluate the data.
yes, you're correct. But if we go back to our previous class and we go back to the first thing on the syllabus, what does it say there on the first syllabus? Like, all models are wrong, some are useful, right? Like, no statistical model will do a good job at any concept, much less such a complex and fluid concept such as happiness, right? So even the simplest of concepts, such as wealth, how much money you have, is itself a complicated concept. Because again, is it money that you have? Is it, like, there's a lot of people that are confident that they'll make money, and therefore they spend a lot of money. Right? So they might not have a lot, but tomorrow you wait 3 days and they'll have more, and, right? Or there's people that save a lot of money and they have a lot, but they don't necessarily make a lot. So people's perspective of money is very fluid and it's very difficult to just pinpoint. So that's even a relatively simple concept, wealth, which just has to do with ownership. On very complicated ideas, such as happiness, I would say statistics is a very unsuited tool for the study of happiness. The only reason I use it as an example is because we all want to be happy. And the minute I say happiness, I get a buy-in and attention. Right? Because in the back of your head, you're like, hopefully this guy's going to explain to me how I can be happy. And you're paying attention. Right? I will not explain to you. Right? Because I don't know. If I knew it, I would just be happy myself. But anyways, so you were right. You have to be weary of what exactly you're trying to study, and does that question lend itself to quantification? Right? Remember, in the beginning of this lecture, I said, we have to take a concept and quantify it, turn it into numbers. Some concepts just don't lend themselves to that, right? Because happiness, for example, is much more complicated than how much money you have, right? And your life experiences, like I shared with you that my daughter passed away 3 months ago, right? And it's a life-changing experience. In many, many ways, I'm very sad. In many, many other ways, it has given me a very different understanding of what happiness is. I mean, it really has changed my perspective dramatically, right, as to what does it mean to be happy. And I used to put like you said, I used to put way more weight on money than I do now. 3 months ago, I would give up every single dollar that I have to spend, not to have her back, just to spend one more day with her, right? So these things change. So you, again, going back to your question, you are going to have to think very carefully about whether or not this is a good measure of what you're trying to get. Even if you give a scale of 0 to 10, happiness, 0 to 10, right? Somebody answers a 12, you throw that away because they don't even know how to read the scale, right? Now, somebody gives you a 7, you're going to take it, right? Well, how do you know that that person really understands what that 7 really is? Right? Maybe they're happy that day because they're high on oxy, right? Who knows? I mean, do you have the heart to ask you, what's your happiness level? And how much oxy did you take? Is it 180 or just 90? Right? Or whatever. Are we good? I want to take a break, guys. But I do want to answer every question that you have. Are we good? Go get yourself some oxy. 10 minutes. We'll be back here.